Alright, Bismillahirrahmanirrahim. Assalamualaikum and very good day to everyone. Today we continue our lecture today on the X-ray fluorescent analysis. As I think everyone aware that we are now moving to another chapter, which still utilizing the X-ray as the source of the main characterization technique. Right. X-ray fluorescent analysis, also what we call is X-ray fluorescence spectrophotometer. That is the instrumental basis. Okay. By principle, XRF will tell us about the principle of having the elemental composition of one material. So, you as a material scientist and a training will be able to explain the principle of XRF, how the machine works, how the instrument will be able to tell us on the characteristic of the materials. Okay, in this case, the component or element of one material can be revealed from the X-ray analysis, which we will be referring to the X-ray SRF spectrum. By principle, when an element is placed in a beam of X-ray, the X-rays are absorbed. The absorbed atoms become ionized. For example, due to the X-ray beams ejects the electron in the inner shell, and the electron from higher energy shell, example the L shell, then fall in the position vacated by dislodged inner electron and emit X-rays or characteristic wavelength. Okay, this process we call as X-ray fluorescence. Okay, and the wavelength of fluorescence is characteristic of the element being excited. So the wavelength of the fluorescence is the characteristic of the element that has been excited. Measurement of this wavelength enable us to identify the fluorescing element. So every single element will fluoresce differently. Why? Because every single element will have different electronic configuration. How many electrons that one element will have will be different from one to another. Let's say carbon and oxygen and nitrogen. All those are having different electronic configuration. Electronic configuration means the amount of electron that will have in the specific arrangement of the electronic position. Okay, the intensity of the fluorescence depends on how much that the element is in the X-ray beam. Therefore, measurement of the fluorescence intensity makes possible for the quantitative determination of an element. So the process of detecting and analyzing the emitted X-ray is called X-ray fluorescence analysis. In most cases, the innermost, which is the K and L shells, are involved in XRF detection. A typical X-ray spectrum from an irradiated sample will display multiple peaks of the different intensities. So these different intensities will carry different concentration and different character. Okay, this is an example of a spectra which was taken using MTEC XR100CR. This is the spectrometer that has been used. The X-ray detected 20 microseconds shaping time of optional feature. So what we can see from the spectra is that there is on the y-axis is the counts in log, meanwhile on the x-axis is the energy. Okay, so the characteristic X-ray are labeled as K, L, M, and N to denote the shells they originated from. Okay. So another designation that can be used here is that we have alpha, beta, gamma, which made to mark the X-ray that originated from the transition of the electrons from higher shells. Okay, hence, and here, for instance, K alpha X-ray is produced when a transition from an electron from L to K shell, and K beta X-ray is produced from a transition of an electron from M to a K shell. Okay, I hope you can get some idea how the notion of the using like K, L, or alpha and beta. Since within the shells there are multiple orbits of higher and lower binding energy electron, a further designation is made as alpha 1, alpha 2, beta 1, and beta 2, and etc. This is to denote the transition of the electron from these orbits into the same lower shell. Okay, let's see, this is like a diagram of an electron. If you see an electron in the K shell, okay, an electron in the K shell, look at the K shell, which is the most inner part of the atom, is ejected from the atom by external primary excitation X-ray. So we have some sort of huge amount of energy, which is the from X-ray tube possibly, hit the sample, and we can see that the electron is ejected. Okay, so therefore the vacancy is now created. Okay, and if you see that an electron from the L or M shell jumps into the field, jumps in to fill in the vacancy. Okay, if you see in the figure, the electron from L to L or M can jump in to fill the vacancy. Okay, because the vacancy is already created. The electron that ejected was called as photoelectron, but now we are talking about the vacancy. Okay, in the process, while it is jumping from the outer shell to the inner shell, for instance, in this case, it emits a characteristic X-ray unique to this element, and it in turn produces a vacancy in the L or M shell. Okay, I hope you are still with me. And then when a vacancy is created in the L shell by either the primary excitation X-ray or by the previous event, an electron from the M or N shell, which is the outer one, jump in to occupy the vacancy. Okay, because there is a vacancy, definitely should be filled in to make the system stable. Okay, so in this process, it emits a characteristic X-ray unique to the element, and in turn produces a vacancy in the M and N shell. Okay, so those are in the previous ones, those are the occurrence or sort of what we call events that can emit the X-ray. Okay, now we are talking about what is actually can also happen when we have those transition. Now we are talking about OJ electron. I think we have covered this part in the previous lecture when I talk about X-ray photoelectron spectroscopy. So again, this is like some revision. The excitation energy from the inner atom is transferred to one of the outer electron, from inner to the outer electron, causing it to be ejected from the atom. And then this process is a completing process to SRF. So this is an OJ electron. Okay, now back to the story. Axis fluorescence spectroscopy in general provides a means of identification of an element by measuring its characteristic X remission length or energy. Okay, This method allows the quantification of a given element by first measuring the emitted characteristic line intensity and then relating this intensity to the element concentration. So the energy of the peaks leads to the identification of the element present in the sample, which is the qualitative. Qualitative, it means that you know there is a carbon, there is a nitrogen, and etc. That is one of the examples. There's a sulfur over there. You're talking about quality. Quality is about the present. If you're talking about quantity, it's how many, how much that you have. While the peak intensity provides the relevant to the absolute element concentration, which is we call as semi-quantitative or qualitative analysis. So when talking about XRF, it is a rapid analysis, non-destructive. You don't have to destruct your sample. Your sample will be as it is. No spectrum is affected by chemical bonding. We are not talking about chemical bonding over here. We just to confirm what are the element and how much it is present on the sample. Easy analysis of the element among the same family elements, high accuracy, easy qualitative, and easy sample preparation. So element oxygen can be analyzed by oxide's content is estimated by assuming the sample contains certain oxide. Okay, we can actually analyze the element of oxygen, but for oxide's sample or oxide content, we have to use an assumption. Consequently, oxide content is estimated result because SRF can only determine elements. Elemental carbon and sulfur also can be analyzed, but not CO3, SO4, or CO3. So those are the things that we are talking about. We are talking about the identification of elements, okay, not about the oxide. But due to some advancements, there is a setting and some sort of optimization of the process in which that now we could be able to determine the oxide concentration using SRF, but it needs a certain modification of the setting in which that we do some calculation and etc. Okay, if you see, this is a schematic diagram, a figure of X-ray fluorescence spectrophotometer. Still, we are using the principle of the n lambda equivalent to 2d sine theta. It's like a principle of X-ray, but because X-ray is a part of the source in here. So this is the layout of the XRF. First, we have the X-ray generator part, started from X-ray generator to go to the sample chamber, later to collimator, and finally to spectrometer part. Okay. At the spectrometer part, we start to have the analyzing crystal, collimator again, and finally we count and record part. Okay, so though there are some explanation about each part of the component in XRF instrumentation. Okay, this is the X-ray. I think we have covered this one. X-ray is well understood at every single characterization technique that needs it as the main sources. Okay, there are two types of X-ray tubes, side window or end window. These are different functionalities, but sort of like they should be there to control the production of the X-ray. Okay, and there is like side window and end window. What sort of target materials that's suitable on using this one? What are the grounding method? It could be anode or cathode. Grounding, it means that to stabilize the charges. Okay, and we have some cooling water system and how we use type of water. Okay, I'm moving on to there you go. We have the analyzing crystal. Okay, and then we have some. I think this is the basic because we understood and we have actually explained to you during the X-ray principle. Okay, this is the qualitative measurement result. You can see that this is the intensity versus 2 theta. This is like the based on the X. This is a spectrum. Fluorescence spectrum, but it tells us about the in the perspective of the degree of the X-ray. Okay. So those are the sort of like how the XRF is being used as one of the qualitative and quantitative analysis. Okay, so this is a quantitative analysis. Definitely there is a intensity and required because SRF is a reference method. So when you say it is a reference method, we have to establish the standard. So establishing the standard required for quantitative result. Okay, so this standard is being analyzed, intensities is being obtained and normalized to a certain extent to ensure that you are taking the right numbers of the concentration. Okay. So this is normal. I think you have learned this before. Sample preparation is very easy. Let me explain a bit of the sample preparation. We need to first grind your sample until we get them using the less than 400 mesh, if possible, to get the very, as tiny as possible, to minimize the scattering effects. If you have like a bulk sample, so it will lead to the scattering and then your data is not that accurate. So, and then pressing hydraulically or manually, you have to make it like a compact, okay? And then if your sample is solid, that one previously, if your sample is powder, okay? If your sample is solid, you need just a flat surface, okay? Liquids should be fresh when analyzed with short time analysis if sample is evaporative. Okay, sample should not stratify during analysis. Sample should not contain precipitants. Solid analysis should show settling trends with time. In a bigger perspective, XRS has been used in many applications. The last 2 decades, the development of X-ray detectors has established the XRF method as a powerful technique in number application field, including number 1, ecology and environmental management. Let's say you want to analyze and determine how many heavy metal in the specific of like by the sea. Okay, you want to see how much the beach is being contaminated by the heavy metals because it's being close to the oil and gas platform. Okay, geology and mineralogy, you want to know what are the content of the sulfur, what are the content of the carbon, and etc. Okay. So metallurgical and chemical industry, quality control of raw materials, production process and final product, and etc. Jewelries. So one of my students, Adlan, he's doing his PhD. He basically is measuring the purity of a gold. Okay, so we know that all the jewelries are very precious. And what are actually the methods of identifying the fake gold or the real one? How? So what Adnan is doing is he is actually optimizing some sort of algorithm comparing of the assay method. So how to ensure that your goal is real one is that you have to make a you have to make a system, which is that system or the process to determine the percent of the gold is by having the fire assay. So fire assay is the method, the very conventional one. Nowadays we are using a fire assay will destruct your sample, so your material is gone. But SRF is an alternative to actually giving some sort of information. This is highly possibly will be accurate to a certain extent. But in here, what we are focusing is that we want to establish, we compare the goal from one manufacturer to another. We have set of data of the percentage of the gold that are available in one sample. For instance, we have more than 20 sample, I guess. So we see the trend, how the different of the quantity of the gold, quantity of the gold in that particular jewelry. So once we know what is the trend or the key or any factor that can be a foundation to improve the accuracy of the XRF. One thing that we realize is that when you are measuring the XRF, using XRF, the problem is that there is the redundancy of peak. It means that the gold peak can be redundant with another metal. So in here, the manufacturer or people who is not that honest can take an advantage to replace the composition of the gold with something else, because by end of the day, at the end of the day, you can see the peak is putting some sort of range at the same value. So those are the things that we are trying to counter. Okay, food industry, food chemistry, you want to know how much your food contaminated with other unwanted element and etc. Okay, so I guess that's all for this session. I wish that we could have a session to have sort of interaction. So I hope we can have this through our chat in the chat room by WhatsApp. Thank you very much. That's all for today. Assalamualaikum.